Hello friends, today we are going to discuss the full wave rectifier the practical way. Now, before we could start our discussion on full wave rectifier, we would first like to understand the circuit, what are the components required and what are the measuring instruments required. So, let's start our discussion about full wave rectifiers. Okay. What do we need? We need a step down transformer, the primary side will be connected to the AC source. This is live and this is neutral. It is a iron core type, hence these lines signify that it is an iron core type transformer. Now we have a center tapped transformer. Obviously, we will get a tapped right from the middle of the secondary coil. We are calling this the secondary side. Now the transformer that we are going to use, the output written is 12 0 12. The current, the maximum current that it can provide at the secondary side is 1 ampere. Okay, now to make a simple full rectifier, what we need is a PN junction diode. Now, a PN junction diode is nothing but a junction between a P-type and an N-type. Now, we are going to use a power diode, but in our situation, since the current requirement for the testing purpose is very low, we'll be concentrating our discussion only with 1N4007. 1N4007. Now one thing I would like to stress is the 1N here means it's a one junction device and these are international standards. Now this is our diode 1. This side is the P-type, this side is the N-type. Rather, this is the anode and this is the cathode. And some of the books you might have seen, they have written C. I prefer to write K. It doesn't matter. Okay. Now the next, the diode. Again, it's a 1N4007, and this particular diode, again, the P-type is again connected to this terminal. Let me label this terminals as X, let this be Y, and let this be Z or Z. Now what we need to do is we need to connect both the N-types together. Now when we connect both the N-types together, from here what we will get is the rectified output. Now this is our common terminal and it will remain the common terminal, and we will connect a load resistor to complete the circuit. We will get a load voltage across this and we will call this VDC. We will label this as RL, and the value that we are going to use will be greater than 1 kilo ohms. Now, we can measure the output voltage using a simple digital multimeter. We can set the dial of the multimeter in the DC range, and the voltage that we will get at the output is nothing but the average voltage. Now, our discussion here right now is without filter. Now, let's see how the entire circuit works. Before we move on to the entire circuit and how it works, we will take up the devices one at a time. Now, let me also write down the equipments or the devices that are being used here. Now, TX is the step down transformer. Now, when you visit the market, you will have to basically ask those guys who are selling these products. They will ask you what type of transformer it is. You will have to say it's step down transformer. The next thing that they would like to know is what is the output voltage. And now you will have to say it's 12 that is a center tapped transformer. Next thing they will ask you is the current capacity. In our case, it is 1 ampere. So these are the two things that is the basically we need to tell those guys. Now, what is the next one that we are going to use? We are going to use PN junction power diodes. In our case, we use 1M4007. You can use some other also, like 5402. You can use 5408. You can use 6 amps diodes also. But for our discussion, we restrict our discussion to 1M4007. Now, what is the next thing? The next thing that we require is a wishboard. Now, I'm using wishboard because I'm going to experiment it out. I can use different circuits. I can change my design anytime I want. But if you people want to have a power supply, an unregulated power supply, you can obviously go for a board. Now, what is the next thing that we need? The next thing that we need is a digital multimeter and a DSO. Well, DSOs are a bit costly. We can use the DSOs to check the waveforms and also calculate on the output voltages, but this is optional, and if you don't have, it doesn't mean that you can't make a half wave or a full wave rectifier. I'm going to use this to show you the waveforms so that the theory that we know corresponds to the practical that we are going to do. Okay, now let's see how the center tap transformer works. When we use a center tap transformer, we apply the 220 volts AC to the primary side. Well, my discussion is related to the AC source that is being used in India. There may be other countries who are using lesser voltages. It may be 110. Doesn't matter. If it is 110, you need to provide that to the primary side, and you will get the possible outputs, the available outputs at the secondary side. So the primary side is basically the AC source that is available in your household. Now, the secondary side, the terms are lesser compared to the primary ones. Now, this is 0 or the CT or the common terminal. Now, what happens when a simple transformer is first switched on? Now, when a simple transformer is switched on, the AC source is applied to the primary side, and due to mutual inductance, a voltage will be available on the secondary side. Now, on the secondary side, what type of waveform you would expect? Now, in our household, what we get is a pure sine wave. Now, when a pure sine wave is applied to the input side, the voltages that are obviously shown here are nothing but RMS value. So, if I am considering the secondary side as 12, 0, 12, then obviously this voltage rating is nothing but RMS voltage. Now, when we were talking about the waveform, the input waveform is like this, and the output waveform at the terminals X, Y, and Z will be, well, one thing you need to know is the common terminal is at which we measure the voltage. So it is essentially at 0. So the waveform at X should be like this. This is the positive half, this is the negative half, this is the positive half, this is the negative half, this is the positive half. So if I divide this, say this, let this be T1, let this be T2, let this be T3, let this be T4, and let this be T5. So this was at X. Now let's see how will it look like when it is Y. I'm sorry, at Z. So this is the waveform that will be available at Z, and this is the waveform that will be available at X. We'll see that using the DSO also. Now what happens is, when this is at the positive side, it will be at the negative side. Now this waveform may be the voltage waveform, it may be the current waveform, doesn't matter. So if I consider this to be the current, then I, and this is the time. So now this is the output of the transformer that we will expect when we switch on the transformer at the secondary side. Now let's move on. What will happen if we connect the circuit? Let's see. Now let's see about the case 1. Case 1. Now we have the circuit where the secondary side we have the diodes, we have the load resistor and let's consider the waveform which is between 0 to T1. So if the voltage is between 0 to T1, then at X we will get a waveform like this, which is essentially positive. It is between 0 to T1, and right at that moment between 0 to T1 we will get a negative one here. It's said. Now what happens? Now we have two diodes. Now this side is P and this side is N. This side is P, this side is N. Now what happens is, since this terminal is essentially positive with respect to this common terminal, what happens is the diode, the P side, is at the positive side connected to the positive potential, and the N side is connected to the common terminal via arrow. So this particular diode, the D1 diode, is forward biased. Now let's see what happens to diode D2. Now between the time interval 0 to T1, the 12 which we are expecting here is in the negative side. It's in the negative side. So when it's in the negative side, the P type is essentially biased to negative compared to the N type, which is connected to the common terminal which is at 0. So 0 is more positive with respect to the potential at Z, hence this diode will not function. The current that we will expect will flow from this side through the load resistor through, and it will complete through the common. Hence we will expect a current to be flowing this way, which will again, okay, let's call this ID1, which will again cause a potential drop across this, making this terminal, say we'll call that A, positive with respect to this. Hence the output voltage that we get is VDC. Okay, now let's take up the second case. Case 2. What's case 2? Again we have the transformer. We have the two diodes. Both the N types are connected together, and we will measure the voltage with respect to the common terminal. We have a 12 here, we have a 12 here, we have a live, we have a neutral. This is D1, this is D2. We have load resistor. Now we are going to discuss when the X and Z are between the time interval T1 and T2. So between the time interval T1 and T2, this is negative, this is positive, that is X, Y, and Z. Now what happens? If we consider the diode D2, the p-type of it is essentially connected with higher potential with respect to the n-type. Hence, this diode is forward biased and the current will flow from the side. Please mind, please check the direction of the current through this. Get back like this and complete like this. Again, the current flows from A to B, making this side positive with respect to this. This current is because of the diode D2. What happens to the diode D1? For the diode D1, this side, the P side, this is the P, this is the N, this is the P, this is the N. The P side is negatively biased with respect to N, hence this will not conduct. So now if we look at the output which is available between A and B, we can see that one of the diode conducts between zero to T1, that is the diode D1, when diode D2 is non-conductive. Similarly, between T1 and T2, the diode D2 is conducting when diode D1 is off. The same thing continues, and what we get is a rectified output for both the cycles. Hence we will call this as positive full wave rectifier. So now let's check this out and how we can implement this using the simple components that we have discussed. Now before we move on from there, we will again have to check certain things. And what are the things? Now before we move on, we also know that when the circuit is complete and when we are measuring the voltage is the average voltage. Now Let's do some calculations and we'll see whether that holds true or not. When we measure the average voltage for a full wave rectifier, that is nothing but 2 Vm by pi. Now what is 2 Vm by pi? Whereas the Vm is the peak voltage. How it is measured? Peak voltage is nothing but Vrms into root 2. Now Vrms is the value that will be measured at the output of the transformer. Now in our case we have a 12 transformer, but practically what happens is when we use the transformer, depending on the input voltage, the output voltage varies. So even if it is written 12, you may not have a 12 output. So the RMS value that you are going to measure is this or this, and we will measure the practical values using the multimeter. Okay, now let's do the calculation theoretically. Now what will be the Vn if it is 12 into root 2? Let's do it quickly with a simple calculator, scientific calculator. Now we know 12 into root 2 is nothing but 16.970. Now what would be the average voltage? The average voltage would be 2 Vm by pi. We can write this as 2 into 16.970 divided by 3.14. Now that is 92 divided by 3.14. What we will get is nothing but 10.88. Now this is the theoretical values that we have assumed. Vrms value is 12. Now when we will do the practical and then calculate the value again. So I'm keeping it okay. So we will consider the practical values. After constructing the circuit, we will use the digital voltmeter and measure the actual voltages. Now okay, now let's start the practical. For reference, we'll keep this circuit with us. Now, the first thing that we'll bring up is a step down transformer, and we can see it is a center tap transformer. 3 wires are connected. One is connected to 12, other one is 0, this one is 0 or the center tapped, this one is another one, another 12. So it's basically 12, 0, 12. I'm only showing you the primary side, secondary side of it. Now what we will do is we'll take the common wire, connect it bottom side. Now this wire the common wire has been connected here, and one of the wire will be connected here and the other one here. So one of the 12 is connected here, the another 12 is connected here. Now we have X here, Z here, and Y here. What we need to do is we need to connect two PN junction diodes. Now we have two PN junction diodes. Both the PN junction diodes are having one silver band corresponding to cathode and the other one is anode. So let me connect the p-type with one of the wires of the transformer. Take another one, connect a p-type here with the another side of the transformer, and we can connect both the terminals, both the in types together like this. So this position is the L dash. Okay. Now before we start our experiment, let us check what will be the waveform available here and here using a simple DSO, that is a digital storage oscilloscope. Now before doing that, we'll first see the probes that are available with us. We have two probes. Connect both the probes to 1x mode. This is the 1x mode. Here is the 1x mode and this is the 10x mode. So we'll connect that to the 1x mode. This is the return wire. These are the two wires which will be used to get the signal. Now what we can do is we'll connect one wire here and connect the return wires to this. Okay. Now connect one of the terminal here, one of the terminal here, the other terminal here, and we will try to check the output voltage which is available from the CR. Now as you see that we have connected one of the terminals of the probe to one of the transformer's input, as well as the another probe to the another transformer unit. Now I have also mentioned earlier that the phase of both will be different. It is evident from the CRO. As you can see the waveform, when it is at the peak, the other one is at the negative. When it is at the negative, the other one is at the positive. Hence we can see that the phase of the signal is completely out of phase for both the terms, for both the outputs of the transformer. Now what we will do now is we will just remove one of the output and connect it to the output of the full wave rectifier. See, what we have done is we have taken one of the probes connection to the output of the full wave rectifier. Now let's see the waveform. Here we can see that this is the one cycle that has been rectified. This was the positive cycle, it has been rectified. The negative is also being rectified, and hence we get a full wave rectifier. Okay, now let's move on and calculate the voltages. How do we do it? We will use a simple multimeter and check the output voltage. We have taken the multimeter, connected the negative probe to the ground or the common terminal and the positive terminal to the output of the rectifier. What we can see right now is the output voltage is 12.78. Okay, the voltage that we expected was 10 point something. Let me take that sheet for you. Okay, So what we have got right now is 12.76. So presently my output voltage that I'm getting is 12.74. The voltage that we expected was 10.80 when we assumed the output voltage of the transformer was 12. But what we can see is it is 12.74. Definitely we are having a different voltage at the output. So what we will do is we will measure it. Now the voltage is 14.3. What we have received is VRMS is 14.3. So if you calculate the value, it is 20.223, and what we get is 12.88. Now let us switch back to the output and measure the voltage. As we can see, it is showing around 2.65, which is more or less equal to 12.88. Thank you for watching the video. I hope you have a small experience and a good experience about how to design a full wave rectifier and how to calculate the average voltage that we get without filter at the output of the full wave rectifier. Thank you. If you like the video, please subscribe and share. Thank you very much.